Permeability is the ability of a reservoir rock to allow fluids to flow. The higher its value, the easier it is for fluids to flow. It is measured on a rock core sample in the laboratory. When the test is done with only one fluid phase present, the measured value is referred to as the absolute permeability. Average values of the absolute permeability in millidarcies from several reservoirs are shown here. The engineer needs to know the distribution of permeability in a reservoir so that in response to the production of fluids in some wells and perhaps the injection of fluids in others, he can predict both the direction in which the fluids will move and their relative flow rate. We observe that ideally we would have both high porosity and high permeability in our reservoir. High porosity and low permeability means a low production rate for a long time, while a high permeability and a low porosity means a high production rate for a short time. When only one phase, say oil, is present in a rock sample, we measure the absolute permeability. Now, if we add a small amount of another phase, say water, the permeability to oil will decrease to a lower value because of the interference of the water phase. This lower value of permeability is referred to as the effective permeability, and its value depends on the relative amounts of oil and water present. Its highest value will be equal to the absolute permeability when only oil is present, and its lowest value will be zero, a condition that occurs when so much water is present that oil no longer flows. If we divide the effective permeability by the absolute permeability, we obtain the relative permeability. It has a range from 1.0 down to 0. The value of relative permeability of, say, oil depends on the relative saturation of oil and water in the rock core sample during the laboratory flow test. It is convenient to show this relationship by plotting relative permeability on the vertical axis of our graph and water saturation on the horizontal. The range of each is from 0 to 1. Normally, a reservoir rock has a finite water saturation referred to as the connate water saturation. It is always present in the reservoir and interferes with the flow of oil. If we measure the permeability to oil on a sample core under these conditions, the resulting point is shown on our graph. As we place higher saturations of water in the sample, the water begins to flow along with the oil. We have both phases flowing simultaneously, and so we can measure relative permeabilities for both the oil and water phases. That for oil decreases, and that for water increases. We finally increase the water saturation and reduce the oil saturation to a point where the oil will no longer flow. This is the residual oil saturation, and the relative permeability to oil at this point is 0. Similar relative permeability curves may be drawn for gas oil, water gas, and oil gas water systems. The value of these curves to the engineer is that they define the connate water saturation and residual oil saturation for that reservoir sample. In addition, they indicate the relative permeability and indirectly the relative rates of flow of each phase at any saturation between the two. By obtaining relative permeability curves from a number of different sample locations in the reservoir, the engineer is able to predict the relative rates of oil, gas, and water movement in the reservoir in response to injection and production activities. They are very important, then, to the proper analysis of reservoir behavior.